Hello again, welcome everyone to the third session of our lecture series. Like I promised you in last session that I'm gonna present an example, or I'm gonna show that it's not necessary that every topological space is a metric space. So let us continue with that. There are many examples and there are many arguments for this thing. What I am gonna do is, like in session 1, if you remember, I have mentioned a example of a topological space called indiscrete topology, right? So let me recall that what is an indiscrete topology. So let X be a set and tau is given by phi comma x. I have written tau suffix int for just saying that it is an indiscrete topology, but let's not mention it here just due to a simple notation. So if you remember, I have said okay, what we call this topological space? Indiscrete topological space is called indiscrete. I think here I should have I. Indiscrete topological space. And like I said to you in first session, this tau we also called a trivial topology, and I have mentioned a few things about the so-called word trivial. So in this session I am gonna discuss about this topology more, and what my claim is, okay, let us write tau suffix int to mention that it is indiscrete topology. int. So what is our claim? That tau, that x comma tau indiscrete topology is not a metric space or a metrizable space, right? So that is our claim. And trust me, like there are various ways, to proceed with this, but I am gonna do this thing in a very different fashion. So let us develop some prerequisites, okay? The approach I am following, as far as we will be going deep into the subject, you will know that why I have told you this approach, and this has something, this is not something very trivial or something we can easily ignore. This is a very important concept. As soon as we will go deep in topology, you will learn that. So learning this approach is a very important thing. So let me start with something called a sequence. I hope all of you know what is a sequence. Let me define it again. So definition. Sequence. So let X be any set. Okay? A sequence in X is a function. a function, say f. Okay, from natural numbers to x. Basically the terms of this sequence is in x, and as you know, we denote a sequence by this notation. Which notation, guys? Like something like this, right? Xn, n in n. Basically what is this? This is f of n, n in n. Okay, good. And definitely xn's are in x. So this is a sequence. So we can talk about sequence on any set. You might have done in real analysis or complex analysis the sequences over real numbers or complex number. Even in metric space you might have done the sequences. So let us little bit, because what we are planning to do here, that in discrete space is not a metrizable space, it's not a metric space. So let us study a property of the sequence which is associated with metric spaces. Before that, let me just recall you the definition of convergence of a sequence. Okay. Convergence of a sequence in R. Let us oh no, I am assuming that you have idea about metric spaces. So let us write for the metric spaces. Okay, in xt. What is xt? It's a metric space. Okay, we say xn converges to x. This is the notation, as you might know. If, what is the definition? Let us recall. For each epsilon bigger than 0, okay, epsilon bigger than 0, there exists a natural number, right? A natural number depending upon epsilon. That is why n suffix epsilon. In natural numbers, such that what is gonna happen? When you take the distance or the metric of this xn and x, this is small or dominated by epsilon, right? Whenever n is bigger than or equal to n epsilon. Very nice. I want to rephrase this definition. What I want to do is I want to write equivalent versions of this definition. So see, I will be doing it in one way, in the forward direction. The converse is up to you guys to verify. Do verify it, okay? So let me write both ways. For each epsilon bigger than 0, there is a natural number, an epsilon, such that I'm just rephrasing this using balls. So such that xn belongs to the ball centered at x of radius epsilon. Ball centered at x of radius epsilon. Whenever, or in other words for all n bigger than or equal to n epsilon. I hope the one way is clear, and also the another way also. I think it is clear. Now let us again rephrase it. How can I do it? For each epsilon bigger than 0, again the first statement would be same. There exists natural number such that, let us see, okay, let's not write this, I'm sorry. Let us write a different statement here. So what's the different statement is? For any open set U, for any open set U in X, such that X is in this open set U. Okay? There exists again a natural number depending upon this open set U, such that what is gonna happen? Think for a moment. If you are thinking this, then you are right. Xn belongs to U for every n bigger than or equal to this nu. Like I told you, I will do the one direction, the forward one. So let me give you the justification for the forward direction. The converse is up to you to verify. So let us verify. This direction. My arrow is like this. So from this one to this one. Okay? I mean this one to this one. That's what I am gonna verify. Okay. So let us assume the hypothesis. So let U contained in X be open. I hope I have told you this notation in session 2. X is metric space, remember. And X belonging to U. Okay? What you have to show, guys? To show there exists a natural number such that this whole thing will happen. So let me rewrite it. Okay. Now, very good. Let us see how we can show this. So X is in U, right? And U is open in X. Apply the definition of open set around the point U. So what it will imply? This will imply there is R we usually use. Let us use epsilon bigger than 0 such that what should happen? The ball centered at X of radius epsilon is sitting inside U, right? So ball is contained in U. Of course, with respect to the metric D. Now guys, let us revisit our hypothesis. This is our hypothesis, right? For what we are doing. We have an epsilon, we have sequence xn, we know that it is converging to this, basically this thing is true. So what we can say? There exists. This is by hypothesis. N in N. Now this N in N depends upon what? Of course the open set U, then epsilon. So U such that what will happen? Ball centered at what? Xn of radius epsilon. This would be contained in what? This would be contained in what? U. For every n bigger than or equal to nu. Right? So see what we have finally. Let us see. Clearly, if you observe that Xn belongs to this ball. Okay? So let us club this thing. We have an open set and a point in it, x in u. Then there exists a natural number nu such that Xn belongs to u for every n bigger than or equal to u. So you see, we are done. Hence we are done. I'm writing it. Please do the converse. Please do converse part. You can do it similar only. Now I wanted you guys to observe something. If you see this definition, I mean this one or this one, these two talks about that Xn is coming closer to X, right? That's what they talk about. So they are sort of limiting concept. Why? Because Xn is coming closer to X. In some fashion, in a fashion. What is that fashion? Basically this thing. That entirely after some point all terms will be at most epsilon distance apart from X. Good. But you just forgot everything and see this definition. What I am circling now. Just forgot everything, proof and all. Just see this definition of convergence. We are just dealing with some open set. Does it contain particularly d or distance? No. So I will revisit. Let me define. This doesn't contain, if you see distance. I mean, you cannot see d. And can you see d anywhere? I will come to this point again. Let me have one more definition, which I should have defined earlier, but I haven't. So what's the definition? Let X tau be a topological space. Then you see, in last session, before that I have told you I will give you another motivation for the definition of topology. So if you see, the open sets in a metric space are forming topology, right? So they have those three properties. Phi and X should be there, arbitrary union and finite intersection. So this is in general we are defining for any collection tau. If that has three properties, we are calling it topology. So it is very, very natural to call what I am gonna do now. Then members slash elements of tau are called, can you guess? 4 seconds. Open sets. So basically, for u in tau, any set u in tau, we say u is open in X with respect to what? Topology tau. You see, that is what I told you in first session, that this example of metric space can be also treated as a motivation. We are just generalizing the families which have the properties like open sets in metric space. And same thing, so now we have, complete thing. So the members of topology are called open sets. Okay, so this is what? Open sets in topological spaces. Right? Like I mentioned earlier, if you have any questions, please ask in comment. I will be replying as soon as possible. I would be happy to have conversation with you. So if you are confused with any concept, so read it, understand it, digest it. Okay, let us continue. Now, let us have one more definition. Convergence of a sequence in topological spaces. Okay, so now you see I have done some equivalent thing. This will make sense here, right? Let me write it, okay? This thing will make sense. So how to begin with? So let xn be a sequence in X tau. Basically, this thing, xn belongs to X. Why I have written in bracket tau? Because I want to specify the topology, tau topology. Good. So let xn be a sequence in X tau. We say xn converges to X in X tau or in X, or you can also write like this, or in X with respect to tau, the topology tau, if for any open set U containing X, open set U, what it means, that is U is in tau, such that X belongs to U. What we must have, guys? There exists a natural number such that entirely after this NU is a threshold, right? You know this English word threshold, or Google it or refer Merriam-Webster's if you don't know what is threshold, like beyond something, or limiting thing. So Xn will be in U for every Nn, n bigger than or equal to this Nu. Good. So you see, here, okay, I will make a note in AND. So let me proceed. So this is the definition. It is not complicated. See, this is just motivated from this thing, like in metric space, like in topological space. Just the difference is, as I told you, not every topological space is a metric space. I mean, there might not be a distance. So if there is no distance, you cannot talk about limit kind of thing. So you see, what point I am gonna make, I will mention it later on, okay, as a remark, that convergence of a sequence in general or in topological spaces is not a limiting concept, because it is not associated with distance always. Okay, let me proceed. I will make it as a remark in the end. So let me just recall a result from metric space. I am not proving it. Now, remember guys, if you don't know the proof, you should learn it, okay? So, what is the result? In a metric space, a sequence can converge to at most one point, right? I think you remember this. You use triangular inequality. You take, let's say, xn converges to 2 point x and y. Okay, just write the definitions and choose the maximum of the two thresholds for xn converging to x or xn converging to and xn converging to y, and then consider d of xy, I mean distance of xy, and then just apply triangle inequality there. You will get this, that x is equals to y. So if a sequence converge, it will converge to only one point, okay? Good. Now let me finally consider this. Consider the topological space. Which topological space? So let X be a non-empty set. Okay, non-empty is sufficient, but just to make the thing interesting, let X is uncountable. Note that this is just to make things interesting. Good. Consider x along with indiscrete topology. Recall what is indiscrete topology? Tau int is equal to phi comma x. Very nice. Now, let xn be any sequence in x. Of course, with the indiscrete topology, that space I'm talking about. Okay? And x belong to x be any point. See what magic is gonna happen. What is my claim? Xn converges to x. Oh wow, you see? This sequence converges to every point of, every point of this space. In fact, all sequences in this space converges to all points. How many of them are? Uncountably many. So let us see the proof. So what you have to do? According to the definition. This is the definition. This. So you have to take first of all open set which contains x. So guys, only open set which contain small x's, capital X only. Why? Because phi and x are only open sets. In x with respect to, of course, the topology is important, indiscrete. Good. Also, xn belongs to x for every n in n. You see, xn is already in x. And for every open set, which is only x here, which contains small x, there should be a threshold. Beyond that, every term of the sequence should be inside x. Here what's happening? Every term is inside x. So what this means? Xn converges to x in this topological space. Alright? Now, let us call this something. Which this? Star. So by star, x star and t cannot be metrizable. Why? Because if it is a metric space, guys, then you see what will happen. A sequence should converge to only one point. So you see, the conclusion of the lecture is number one, not every topological space a metric space. Is a metric space. Now I want to draw, so the picture is like this. So if you see, this is metric space. This is topological spaces. This is actually much bigger. I will be like it's too much bigger, I'm telling you. I mean, how much big I cannot exactly tell you, but it is very big. I mean, you will be soon realizing as far as we will go deep in theory. I want to make another conclusion which I have hinted before. Convergence of a sequence can you guess, is not a limiting concept. In general, because you see, this was the space, the trivial topology. That's why I said this is not so trivial. The name is trivial. In this topology, sequence converges to every point. So first of all, there is no distance. So how can we say two points are close? We can only say through the distance kind of thing, right? I mean, there are other ways to say closeness, but the closeness, what I am talking about is, I am talking about in terms of distance. So what point I want to make is convergence is not in general a limiting concept, because the distance is not present there, because every topological space is not a metric space. What kind of convergence? Convergence of a sequence. So I want to end this session or lecture right now, and in upcoming lecture we will be discussing some more example of topological spaces, some more interesting examples, I should say, of topological spaces. Thank you very much for your attention and patience. See you in next session.